We are doing parallel and perpendicular lines. And this one, is it 3 theorems? Yes, there are 3 theorems that all deal with parallel and perpendicular and how they all kind of relate to each other. They all have numbers. Well, that's not true. 2 have numbers to name them. 1 has a name to name it. I'm not concerned about any of it. You can always, in a proof, just state the theorem. Like, if those 2 lines are parallel, then this one's going to be parallel to it too. But if you want numbers, I will give you numbers just because. So the first one is Theorem 3.8. And like I said, please don't spend time memorizing the number, okay? It says this: if 2 lines are parallel to the same line, then they are parallel to each other. Okay, if 2 lines are parallel to the same line, then they're parallel to each other. Here's what it means. If I have these 3 lines, okay, so here's line A, here's line B, here's line C. If A is parallel to B and B is parallel to C, right? So if I mark it, how do you mark lines parallel?
With an arrow.
Oh, that's your hat. I thought you had put that lunch thing on top of your head. With arrows. So if A is parallel to B, and then if B is parallel to C, we would double their arrows there because those are different lines that are parallel. So if A is parallel to B and B is parallel to C, it's kind of like the transitive property all over again. Take out the B and we know that A is parallel to C. Okay, so that's our first theorem. If 2 lines are parallel to the same line, then they are parallel to each other. Any questions on that one? All right, second one is Theorem 3.9. Am I going too fast again? Okay, here it is. Theorem 3.9 says in a plane, because this does not work 3-dimensionally, it does not work in space, but if it's a flat surface, so in a plane, if 2 lines are perpendicular, do you remember that upside down T means perpendicular? Okay, so if 2 lines are perpendicular to the same line, then they are, fill in the blank, to each other. And I'm going to see if you guys can fill in the blank. So let's think about this. If I have a line here that is perpendicular, okay, so we'll say this is line A, this is line B. So A and B are perpendicular. If 2 lines are perpendicular to the same line, so now if I have a line C that is also perpendicular to B, okay, so they're both perpendicular to B, then what are they to each other? What are A and C to each other? Parallel, okay? So if they're perpendicular to the same line, then they are parallel to each other. So we would say if A is perpendicular to B and C is perpendicular to B, then A is parallel to C. Okay, so if they're perpendicular to the same line, they are parallel to each other. All right. Do you guys know Jesus' occupation?
Jesus?
Jesus. He was a carpenter, right? Okay, so we're going to say back in the day, even though they didn't have photography, I'm assuming, someone's drawing a picture and Jesus is making a frame for that picture. I want to know if Jesus were to cut some pieces of wood like this, where this is 45 degrees, and this is 45 degrees, and this is 45 degrees, and this is 45 degrees. Sorry, it's not my best work, but Jesus would have done a good job. Let's say he cuts those 3 pieces of wood, all with 45-degree angles. I want to know, would this side over here be parallel to the other side? Would the 2 sides be parallel if we were to put that together as a picture frame? So if we were to make it look like this, right? Would this side be parallel to that side if those are our measures?
Yes.
Why?
Because the 45-degree angles add up to 90 degrees, which is a right angle, and if both of them are 90 degrees, then it must be equal.
Parallel, right? So 45 and 45 is going to make 90 here and 90 here. And our theorem says if 2 lines are perpendicular to the same line, then they are what to each other?
Parallel.
They're parallel to each other, right? So this is basically saying, would the sides be parallel? And your answer is yes, because they are perpendicular to the same line. Okay? Questions on that? What if one was 70 degrees? What if the angle up here was 70 degrees and this other angle was 110 degrees? Would they be parallel?
No. Oh, wait. Yes.
Because those are same side interior angles that are supplementary, right? So they'd still be parallel. Would it be a squared up picture frame? No, it would sit like this, but they would still be parallel to each other, right? So it's a different way you can look at it. Any questions so far? Okay, I got one more theorem for you and one example for you. Here's our next theorem. This one actually has a name. It's called the perpendicular transversal theorem. What's a transversal? It's a line that cuts through 2 lines, right, is a transversal. So the perpendicular transversal theorem, again, this one says in a plane because it does not work in space. I'll show you why it doesn't work in space in just a second. But it says this, in a plane, if a line is perpendicular to one of 2 parallel lines, then it's also perpendicular to the other. So if you think about it, these last 2 are kind of saying the same thing, just with a different part missing at the end. But let me show you the picture here. Basically what you're saying is if a line is perpendicular to one of 2 parallel lines. So let's say we have these 2 lines and they tell us they are parallel. And then there's this other line that cuts through and they tell us this one is perpendicular. So if this is A, this is B, and this is C, what they're saying is if B is parallel to C, and A is perpendicular to B, then what will be true? So if the black ones are parallel and the one black is perpendicular to the red, what's true of the other black one?
C is perpendicular to A.
Right, then C will also be perpendicular to A. Okay, so that one's very similar to the last one. It's just in the last one we knew the lines were both perpendicular, therefore the lines are parallel. This is almost the converse of that last one. Not exactly, but really close. Let me just show you why it says in a plane. You don't even need to draw this part. I just want you to see the picture. So just watch for a sec here. Okay, let's say I told you that these two lines are parallel, and I told you that, I'm going to give these letters here. I told you that AC is perpendicular to CE. Does that make CE perpendicular to DF? It doesn't. They're not touching each other, right? So they can't be perpendicular. So that's why it says in a plane, because once you go three-dimensional with it, the parallel line's going this way, but the perpendicular going this way does not touch this parallel line over here. So the reason they say in a plane is because of this situation here, okay? Okay, last thing is just a quick proof. It's 3 steps, and the first one is always what? Given. So it's really 2 steps that we got to figure out. So example 2, and then we are done. This one says, given that in a plane, C is perpendicular to B, B is perpendicular to D, and D is perpendicular to A, we are going to prove that C is perpendicular to A. Lots going on here. Let me draw you a picture, and then I'll give you some time to catch up. So this is line D, this is line A, this is line B, and this is line C. And these are all marked perpendicular. Okay, so C is perpendicular to B, that's this one up here. B is perpendicular to D, that's this one here. And A is perpendicular to D, that's this one here. We're trying to prove that the two that aren't touching yet, but the lines keep going, right? So really they are touching. So if we kept this line going, right? If this kept going, we're trying to prove that that's perpendicular. Okay, and it does keep going because it has an arrow on it. All right, so what's your first step?
In a plane, C plus B C is perpendicular to B.
Right, and please don't write it all again, just do this. Okay, and we know that why?
Yep.
It's given. Okay, so it's a 3-step proof. What's going to go here in that third step? C is perpendicular to A. Right? Whatever they're asking you to prove is your final step. So we just need to know both parts of 2 and the reason for 3. What do we know about C and D?
They're parallel.
They're parallel. Okay, we can say that C is parallel to D. Why do we know that they're parallel?
Because they're perpendicular angles
To the same line, right? So 2 lines that are perpendicular to the same line are parallel to each other. That's 3, 9 right there. Okay, so you can say theorem 3.9, or rather than try to memorize a theorem, just say lines perpendicular to the same line are parallel to each other. Okay, so I know right now that C is parallel to D. Well, now, if we think of this as going through here, we have parallel lines, and this one is perpendicular. Therefore, we know that C is also perpendicular to A. Which theorem is that?
Perpendicular theorem?
It's the perpendicular transversal theorem. It's that last one that we did, right? So you can just call that the perpendicular transversal theorem. Or if you wanted to write it out, you could say a line that's perpendicular to one line that's parallel to that same line is perpendicular to the other. It's a lot easier just to write perpendicular transversal theorem, but that's up to you. I know these three are all so very similar, so you probably just want to keep your notes or your book handy so you can look at those as you go through the homework today. But it's kind of like one is the converse of the other is the converse of the other. They're all very closely linked, okay? Any questions on any of those? So pretty much if lines are parallel and there's one that's perpendicular, the other's perpendicular. If lines are perpendicular to the same one, they're parallel to each other, right? It's all just a lot of because these are parallel, these are perpendicular, or because these are perpendicular, these are parallel. Good?